Hey guys, today we are starting chapter 4, which is all about polynomial functions. And here specifically for 4.1, we are talking about how we can graph polynomial functions. Now obviously we've graphed a bunch of different polynomials before, but here we're looking at a more generic term where we're going to be exploring higher degree polynomials. So starting in box 1, just a quick refresher for us on what a polynomial is. We know that a monomial is a number, a variable, or a product of those two things, like 4x or 4x. But a polynomial is a collection of those things. So it could be just a single term, so it could be a monomial, or it could be a collection of them where we're adding or subtracting them all together. A polynomial specifically is in the form a sub n x to the n power plus a sub n minus 1 x to the n plus 1. Really here what we're talking about, a sub n, those are all coefficients. Those are all going to be nice whole numbers. Real numbers. No fractions or decimal, or fractions and decimals are okay. But as long as the most important thing here is that my exponents have to be whole numbers. And they have to be exponents on that same variable. Meaning I can't have any variable in the exponent. I can't have any decimal or fractional exponents. Any of those things would cause me to say that these are not a polynomial. This is not a polynomial I'm looking at. As we get further into it, a sub n, that's always my lead coefficient. That's whatever's attached to my highest degree term. N here is my degree. So again, whatever the biggest exponent is of my polynomial, that is the degree of the polynomial, and whatever variable is attached to it, coefficient is attached to it, is my leading coefficient. And then a sub 0 is the one that's all the way there at the end that doesn't have a variable attached to it. We say that that's just the constant of that polynomial. So this is all review for us from Algebra 1. It's not anything new, just reminding ourselves of some things that we've done in the past. So, when we say that a polynomial is in standard form, we know that it's written in descending exponent order. So as we go from left to right, my biggest exponent term is first, and then I get smaller as I move to the right, all the way with my constant term being the last one. All right, so here are some examples of some polynomials, some of which you're familiar with, some of which are brand new to us. We've obviously spent some time with these top three, our degree 0, 1, and 2, which we specifically call those constant linear and quadratic graphs. Constant graphs, we looked at those back in chapter 1. We were doing our transformations. And then obviously linear and quadratic we spent a lot of time on between Algebra 1 and this year as well, dealing with both of those different kinds of polynomials. And notice here again, my polynomial, it is a polynomial because my exponents are nice whole numbers. My coefficients are all real numbers. The degree, that tells us what the highest degree exponent is, what the biggest exponent is. And then the type is just how we classify that, what we call it. So we call it a constant graph, we call it a linear graph, we call it quadratic. The two new ones we have here are degree 3 and degree 4. Those are the most commonly seen ones. There are obviously much higher degrees, and we can go, as big of a number as you want to, as long as it's a whole number for that degree. But usually after a cubic and a quartic, we could come up with specific names like a pentic or a hexic graph, but they're so uncommon that we don't usually call them by their special names. It's just that we would call it a 6th degree polynomial or a 7th degree polynomial. But a cubic is degree 3, and then a quartic is a degree 4 polynomial. So, first thing we're going to be asked to do is just be able to decide whether the function that we're given is a polynomial. And if it is, then we're going to write it in standard form, identify its degree, type, and leading coefficient. So first things first, is it a polynomial? So check and make sure, are all of my coefficients real numbers? Do I have variables for my base with whole number exponents all the way through? And you can see here for number 1, we don't have that because of this x in my exponent. Because that x is my exponent and not down next to my 3, it is not a polynomial. Moving along to number 2. Number 2, again, same instructions. If this is a polynomial, if it is, put it in standard form, identify its degree, type, and leading coefficient. So here, my coefficients are all real numbers, right? Negative 0.8, square root of 2, and negative 12 are all real numbers. They're decimals or fractions or any of that sort, but that's okay for the coefficients. My exponents are all whole numbers, and my bases are all my variables. So here, this is a polynomial. So I'm going to go ahead and write it in standard form. So if I wanted to rewrite this, standard form again is decreasing exponent order. So my first term is going to be my highest degree term, square root of 2x to the 4th power. And then I go down in exponent, so negative 0.8 x cubed. And then my negative 12, that doesn't have a variable to it, which would be x to the 0 power, is the last one that I write. So that's in standard form. They also want me to identify the degree, type, and leading coefficient. And I just abbreviate that to just LC. So degree, that's my highest exponent. We know that that's 4. The type, that'd be the special name that we have for that degree polynomial, which in this case, a 4th degree polynomial is called a quartic. As in, like, you know, there's 4 quarts in a gallon, quartic, or quartet is a group of 4 singers or performers. And then the leading coefficient is whatever is attached to that biggest exponent term, which x to the 4th has a square root of 2 next to it, square root of 2. So that would be my 3 pieces of information, putting it in standard form. Another thing that we could be asked to do is, given a polynomial, asked to evaluate it for a specific x value, which should be very easy for us. We've done this countless times. It's just that now we have higher degree exponents we have to be careful with. Here we're asked to identify h of x when x equals 3. So the way that I'm going to go ahead and do this, just like you guys would expect, I'm just going to be substituting 3 in there everywhere I have an x value. So 2 times 3 to the 4th power minus 8 times 3 cubed plus 5 times 3 minus 7. And then I just go through order of operations. We know PEMDAS tells me I have to do simplifying inside parentheses first, which all of the insides of my parentheses are simplified. Then we go to exponents next, before we go on to multiplication, division, addition, subtraction. So 2 times 81 is 3 to the 4th power, minus 8 times 27, because that's 3 to the 3rd power, plus 15 times 3 minus 7. So all of those, I'm just evaluating my exponents. Next, it will go ahead and multiply. 2 times 81 is 162. 8 times 27 is 216. 5 times 3 we know is 15, minus 7. And you add all of those up. 162 minus 216 plus 15 minus 7 is a negative 46. So h of 3 equals negative 46. Now, obviously, I didn't do all of that in my head. If you can do that, that's fantastic. I did that ahead of time with my calculator and just have my answer sitting here ready for me so I can go through a little quicker. But feel free and don't be afraid to use your calculator to your advantage. We know that it's there for us when we need it, and you will always be allowed to use it. So don't be afraid to utilize that tool. All right, moving along to box 3. Now, box 3 is a little bit different, and it takes kind of a step back a little bit because it's another information box. In box 3, we're talking about something called end behavior, which really gets into a little bit more of kind of what we kind of start transitioning into upper level math, and we start thinking of things more connectedly rather than as individual topics. So the end behavior of a function describes, just like it says, what happens at the end of my function. So as x gets bigger and bigger and bigger on into infinity in the positive direction, and x gets really, really small in the negative direction for negative infinity. What happens to my graph? What do the ends do? Do they go up? Do they go down? Does it alternate? One goes up, one goes down. Which side does that happen on? So that end behavior is going to be something that helps us graph our functions, because with higher degree polynomials, they don't have the same kind of shortcuts or tricks and stuff that we can do like linear like lines do, like parabolas do, where we have the different forms that it can be. There will be some things that will help us to graph it, and end behavior is one of those things. So as we look through a polynomial, the end behavior is determined by really two things: the degree of the polynomial, and then what the sign of that leading coefficient is. So my degree can either be even or odd. And this is something, again, as you look at more and more examples of it, you realize there's some patterns with the two of them. And if we go back to the examples we're comfortable with, an odd exponent degree, an odd degree exponent that we've covered is a linear graph. An even degree exponent is a quadratic, so a parabola. With even exponents, you notice my endpoints always point the same direction. Right, in the parabola, they both pointed up or they both pointed down. With a linear graph, one pointed up and the other pointed down, so they alternate directions. That's true for any even exponent graph and any odd exponent graph. So anytime I have an even degree, my endpoints are going to go the same direction, either both up or both down. When I have an odd degree, one's going to point up while the other points down. Or it could be vice versa. One points up and the other points down. The leading coefficient tells me what the right side of my graph does. So the right side of my graph, if my leading coefficient is positive, just like the leading coefficient is positive, it's going to go up. If my leading coefficient is negative, the right side goes down. So the way that we'll use that information, this is not something you have to have memorized. This little this picture here, that's not very clear, but maybe it'll be better on the cheat sheet that I've provided for you. Maybe it's just because I'm so far zoomed in. But this is what we'll utilize, and this is kind of how we determine what my graph looks like. In this picture right here, my degree is odd. They point in opposite directions. And my leading coefficient of that polynomial is positive, meaning the right side points up. And in an odd graph, again, if one points up, the other points down. So if we know that the right side points up, that means the left side has to point down. If we had that same leading coefficient, but with an even degree always points in the same direction. So if my right side points up, my left side also points up, because they both go in the same direction. If I flip the other way, if I had an odd degree, but a negative leading coefficient, the negative leading coefficient tells me my right side points down. The odd degree tells me that if my right side points down, my left side is going to be pointing up. And then finally, for my last combination here, if I have an even degree with a negative exponent or leading coefficient, that means my right side points down, my left side also has to point down. So what we'll do is use that information along with kind of figuring out what the middle of my graph looks like to be able to get a decent sketch of some very, very complicated equations. Because you notice here with these, I'm just talking about the end behavior. What I was just looking at is just what happens at the far right side and the far left side of my graph. The middle is kind of the interesting part. And that's where we'll spend most of this chapter, is kind of going through and trying to figure out what are my zeros, what are my intercepts, kind of those important pieces in the middle. So we can describe kind of what shape it looks like in the middle part of it, and then use the end behavior to just continue on and know which direction we're supposed to be going. So as usual, like we always do when we're going through and trying to figure out what a graph looks like the first time around, I'm just going to suggest plugging in some points. So in this case, if we plugged in our values from -2 to +2 into our equation, we're going to be able to see, at least for those middle 5 values, what does the shape of my graph look like, and then we'll use the end behavior to describe it the rest of the way through. So I'm just going to go through just like we had before, like we just did in the previous box 2, and just plug in some different x values to get some y values back out. So as I go through, my equation this time around is x to the 4th power minus x cubed minus 4x squared plus 4. So as I go through here, I'm just going to be plugging in different x values. So -2 to the 4th minus -2 to the 3rd minus 4 times -2 squared plus 4. Well, that gives me 16 plus 8, because that's a -2 cubed is -8. So -8 is +8. -2 squared is 4. Times 4 is 16, so -16. And then we've got +4, so those kind of cancel each other out. So I've got 12 for my y value, -2, 12. Continuing through, -1, and this will take probably about, 30 to 45 seconds if you guys want to skip ahead a little bit and just catch up on me. For those who want to kind of hear me talk through them, stick around and, stay in sync with me. -4, -1 to the second power, plus 4. So -1 to the fourth power, oops, not 4, +1, right? An odd exponent makes it negative, but since we're subtracting, that's a +1. -1 squared is +1 times a 4 is 4. So -4, and then we've got +4. So those kind of cancel each other out, and 1 plus 1 is 2. Zeros, these are always easy, because really any of the variable terms are going to just go away. 0 to any power is just 0. So I'm just left with my constant, which is something that will be useful for us, kind of a shortcut, a trick that we can use is when you're dealing with any kind of polynomial, the constant of that function is always the y-intercept of that function, which I don't know if we ever really addressed in the quadratic chapter when we were going through and graphing stuff, but it makes sense because if your x value is 0, anything that has the variable attached to it is going to be 0. So whatever that c value, or in this case, whatever my constant graph is, or constant number is, the constant, is going to be my y-intercept. So useful for us. Continuing through, for +1, we've got 1 to the fourth power minus 1 cubed minus 4 times 1 squared plus 4, which gives us 1 minus 1 minus 4 plus 4 gives us 0. And then last but not least, 2 to the fourth minus 2 cubed minus 4 times 2 squared plus 4 gives me 16 minus 8 minus 16 plus 4. So those kind of go away. -8 plus 4 is a -4. So we've got all 5 of our points that we can plot. Now, beyond that, we have to look at our end behavior. So again, we need to look at, is it even odd for my degree? And is it positive or negative for my leading coefficient? So lucky for us, our function is already in standard form, and we can see that our degree is 4. That's my biggest exponent, so we're going to be dealing with an even function, or we are dealing with an even function. And my leading coefficient, I don't see anything here. We know it's a 1, but most importantly, I don't see a negative sign out there, so it's going to be a positive positive leading coefficient. So my end behavior, we know, was even and positive. So that tells me, since it's even, they go in the same direction. Positive tells me the right side goes up. So we can just say up on both sides. Now, over here, they describe, hey, look at that, even and positive right next to it. They describe it very funky, very weird. If you look at some of these other notations, like f of x approaches positive infinity as x approaches negative infinity, that's just kind of describing what the left side does and what the right side does. I don't usually utilize that. There's occasionally a book problem that might be thrown at you that it does kind of just talks about the end behavior and describes it in this way. And just know that, again, my f of x is the same thing as y. Positive infinity means up, negative infinity means down. In the case of my x values, negative infinity means left, positive infinity means right. So this is saying the left side goes up, the right side also goes up. Again, we're looking more picture-wise for our graphing stuff, so we know that it's going to go up on both sides. So now, knowing that, I'm going to go ahead and start by plotting my graph, plotting my points. So it was negative, I am just off my graph here. Poor planning, Mr. Barons. So -2 was positive 12. We'll just approximate it right there. And then we've got -1, 4, 0, -1, 2, 0, 4, -1, 2, 0, 4, 1 was 0, and then 2 was -4. Sorry, zoom out here a little bit and take a look at it again. We knew my x values were the -2 to +2. My y values were 12, 2, 4, 0, and -4. So those points right there. Now what we have to be careful of is both sides, again, since it's an even and positive polynomial, both sides point up. So what we have to do is just make sure that after I connect my dots here, that eventually both my right and my left side point up. Which here, I can start out pretty easily, and I'm going to do this in red just to do a different color. I know I can go down. I'm going to go back up to connect my dots. Back down between these ones. And then I have to finish back up. I don't know really where that happens, but for right now, I don't really care how perfect that is. We'll get more specific, like we'll get closer into what they will actually look like. And, you know, we look at different inflection points. We look at intercepts to be able to identify where it crosses the x-axis or the y-axis, so we know more specifically where those important points are. But for right now, you're just finding those middle 5 x values, plugging them in to get our points, and then just making sure our end behavior matches our graph. That is all I have for you for these notes for 4.1. Your homework is on page 162 and 163. We're looking at 4 through 32, just the evens. As always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. And have a fantastic day.